If we say something weird, it'll be on there.
Yeah, it'll be on the internet forever.
Everybody say something
I am murder. Okay, what are my side bounds? Can you see what my side bounds are?
You're not out of it. Yeah. Now you're in it.
Yeah.
Well, like, can you see here?
Yeah.
Yeah? Okay. I'll go from here to, can you see over here?
Yeah. Now you're out.
No.
So like about.
I think.
I can't see your arm. Move your body.
Wait, move that way.
I don't want to see the connection. Yeah, right there.
Right here?
Yeah.
Okay. And then you said half the A, so I got all the way to the top. Okay, so let's start. A particle with a mass of 55 milligrams and a charge of negative 19 microcoulombs is placed in an 8,500 newtons per coulomb electric field directed to the right. What is the magnitude and direction of the particle's acceleration? So here's our electric field going to the right. And we have a negative particle placed in that field, okay? How am I going to do this? Magic? What kind of magic? Okay, I'm going to use F equals EQ, okay? When I take a charge and I put it in an electric field, it experiences a force, okay? So I'm going to use F equals EQ, okay? So my electric field is 8,500. My charge is 19e negative 6. That's micro. Okay? So somebody calculate for me. What is the force that this particle feels? Almost dropped my pen.
What's the equation you're using?
F equals EQ. The force equals the strength of the electric field times the charge that I put in that field. Something we did yesterday.
0.1645.
Yeah.
0.1615 newtons. Okay? Is that my answer? No. Okay? It's asking for acceleration. Alright? How do I get acceleration from force? What equation can I use? Ooh. I can use one of those old ones. Force equals mass times acceleration. Okay? Now, we got to be careful. When we go to plug in our mass needs to be in kilograms. They give us milligrams. Ugh. So, let's convert that real quick. 55 milligrams. How many milligrams in 1 gram? 1,000. 1,000 milligrams per 1 gram. How many grams per kilogram? Another 1,000 grams per 1 kilogram. Okay? So in order to convert from milligrams to kilograms, we need to divide by 1,000 twice. What's that? Right, 55 e negative 6. Okay? So, force equals mass times acceleration. Force is the thing we just found, 0.1615, equals mass, 55 e negative 6, times acceleration. Let me know what you get for acceleration. 2936.36. What? What are the units?
Meters per second squared.
Meters per second squared. There we go. Acceleration. 2,936.36 meters per second squared. Okay? Anybody have any questions? Oh, wait. There's one more question on the warm-up. What is the direction of this acceleration? Skip. Who cares? We got votes for right, votes for up, votes for down, votes for left.
That's to the right, right? To the sun.
Let me remind you of the definition of electric field. The electric field is the direction that a positive charge would go. So which way does it go?
It would go left.
Left. Left. Look, we have a negative charge. Negative charge will go the opposite direction of a positive charge. So our particle is going to be accelerated to the left. Okay? Everybody see why? Because we have a negative particle. Everybody good? Can I erase?
Yeah.
Okay. Erase. Okay. Part R. The above particle is now placed in the Earth's gravitational field. What is the Earth's gravitational field? Anybody know? What number?
This is a specific number.
Yes, the specific number.
It's a very large number.
Not really.
9.8. It's a very small number.
9.81.
Oh yeah. That's so what I said.
The Earth's gravitational field has a magnitude of 9.81 meters per second squared. Okay? So, our particle is placed in this gravitational field. What is the magnitude and direction of the electric field necessary to levitate this particle? Ooh.
I told you it was dark matter.
To hold it still,
I
like.
know that, but like, how would that work?
Okay, how does it work? Let's draw a free body diagram real quick. So we have the gravitational force acting down, right? In order to levitate it, what has to happen? What do we have to have? We have to have a force going up, which is going to come from the electric force.
Does it have to be greater than that?
Did it?
It moved.
It moved? How did it move?
It's like right above the R now.
That's weird. Did it get any of the other stuff?
I think it did, but it looks like it zoomed in. Oh, there it is.
Ah, what happened?
It zoomed out.
Hey, everybody. Oh. Yeah. I'm recording for the band kids.
Okay.
Now you can see up to the W.
Yeah.
There we go. Okay, that should be able to see everything. Can I see the stuff on the side, though? Let's see. Let me. Oh. Oh, why are you zooming in? Oh, because it's touching the metal stapler. Hey, it'll be fine. Okay, so I've got the gravitational force going down, so I need a force going up. That's going to come from the electric force. F electric, right? How are you guys doing over there? They didn't even see me. Hey, how's it going? Okay. So in order for this thing not to move, what has to be true about these two forces? They must be equal, right? If I do sum of forces equals 0, right? 0 sum of forces will give me no acceleration. So Fe acting up minus Fg acting down. These two must be equal. Okay? Do we have an expression for force electric? Do we have a formula for that? We do. We have two of them. Right? K, Q1, Q2 over R squared, and F equals EQ. Which one do you want to use? EQ, because we're looking for an electric field. Okay? So EQ equals, do we have an expression for gravitational force? We do. Anybody remember what it is?
No, the
mg. mg. Okay, mass times acceleration due to gravity. mg. Okay? So that's it. We've got Q, we've got M, we've got G. We're looking for E. So, electric field equals, mass is 5.5 E negative 5. G is 9.81 over Q is that one, 19 E negative 6. So let me know what you get for your electric field.
Oh no.
How's the camera looking?
Good. 28.397.
20.397?
I give up.
20 what?
28.
28.
397.
Newtons per coulomb are units. 28.397 newtons per coulomb. Okay? Everybody good? Real quick before we finish up, what direction? What direction does that electric field need to be?
Away from the gravity.
So what is that? Up, left? Care?
Wait, what was the question?
What direction does our electric field need to be?
Center.
Not going to be up.
Opposite of gravity.
It will be down. Our electric field will be directed down. Why?
Because gravity is greater.
Look, we need our force to be up. Which way does a negative particle go?
Opposite.
Opposite of the electric field. So if we have an electric field going down, a negative particle will go up. Okay? So we need our electric field to be directed down. Doon. Okay? Anybody have any questions? All right. With the rest of the class, what I would like to do, I'm going to draw some charge arrangements, some arrangements of charge, and I'd like you to draw the electric field lines for them. Okay? I'm going to do 3 up here, and then we'll go together. Children, what are you doing? While I'm recording too, now everybody knows how delinquent you are. I'm going to turn around the camera and show them your face. Be like, avoid these people. Do not hire them. Forward to all employers. Okay.
I'll remember not to ask you for my letter.
So the first arrangement I want you to draw the electric field lines for is 2 negative charges side by side. Okay? 2 negative charges side by side. The second one, 1, 2, 3. 3 positive charges in a triangle. And the third one, 3 positive charges and a negative charge in the lower corner. Yes.
Oh, wait, I was touching.
Oh. Remember the rules for drawing electric fields? Number 1, it's the direction that a positive charge would go. Number 2, they go out from positive into negative. Number 3, we can pretty much ignore. The number of lines is proportional to charge. These all have the same amount of charge, so we don't need to worry about that one. Number 4, probably the most important one, electric field lines never cross. And number 5, that other one that I forgot. No, they start and end perpendicular to a surface. They start and end perpendicular to a surface. Okay? So no electric field lines coming out like that. Okay? Always perpendicular. 90 degrees, like that. Okay, so I'll give you a few seconds. Meanwhile, I'll talk to you guys. No, I'm kidding. I hope they enjoy.
You should ask
I was
some awkward
watching the
questions
video,
about that.
Are they watching this from DC?
Hopefully.
Yes, they are on their computer right now in the middle of their trip. Just
This is streaming directly to my phone.
live stream.
They're on Skype with
That's not a bad idea. Skype. What?
Instead of a live
Yeah, if you guys from now on, if anybody is sick, I expect you to Skype your classroom. That'd be amazing. Then, like, nobody would ever come to school again. Skype.
yeah.
Okay, you ready to start to check the first one? Okay, let's check the first one. So, electric field lines go out from positive into negative. So if I drew this normally, I'd have into negative, uh-oh. My electric field lines have crossed. What do Ghostbusters say? Don't cross the streams. Can't have that. So, what's going to happen? Electric field lines can bend. Okay, they can bend. So, these electric field lines are going to bend to avoid each other. Okay? So I end up with something like that. Too much. Down that way, down that way. That way, that way, that way, that way, that way. Okay? So your electric field lines end up forming something like that. Okay? Now I really like this picture. Okay? And the reason is you can see you can see the repelling force, okay? If you have your charges with their electric field lines coming out like this, imagine they're like little metal strips, okay? You have your charges, they have electric field lines like this, they have little metal strips coming out of them. As they get closer and closer and closer, the strips start coming together, but strips can't phase through each other or anything, so they start pressing on each other, okay? And those strips want to go back to where they were, so they like bounce off. Does that make sense? That's how I envision it in my messed up brain. Okay? So you can really see the repelling force from those two negative charges. Does anybody have any questions about the first one?
How do you know how many to like draw for one?
It doesn't really matter. Usually 4 is a good minimum.
Okay.
Like for number 2 and number 3, I'm going to do like 4 each because I don't want to draw that many. But yeah, as long as it's proportional to the charge, that's what matters. Okay, if I draw 7.5 on this one, I have to draw 7.5 on that one because they're both the same charge. Let me know when you know how to draw half a line. Okay, let's try number 2. Okay, number 2, we're going to run into the same issue. Okay, we have positive charges, all 3 positive. They want to repel. So if I drew my electric field lines normally, I got crossing electric field lines. Okay, can't have that. So they are going to bend away from each other. Bend away, bend away, bend away, bend away, bend away, bend away. Ooh, that was a little bit sharp. That's okay. Okay? So you end up with something like this. Maybe a few extra lines here. Notice all these arrows are going out from positive. Okay? So you end up with something like that. Now, I really like this one because what do you notice going on in the center? Jack squat. Okay? Nothing. Nothing is going on in the middle. And here's the reason why. If I look at the individual electric fields, I've got one from this guy.
Teachers, please pardon this interruption.
One
for
from this
final
guy.
afternoon announcement. Students,
One from this
please be
guy.
reminded that today is Tuesday. It is our scheduled tutorial day. Also, reminder to all of
It
our
is Thursday, isn't it?
participating in the Facility Academy. We need those students to report directly to the library.
So,
at 2:45.
I'll try and talk over the announcements.
Please do
I've
not
got one electric field that way, one that way, one that way. What do they do?
Earmark, 10th grade,
They
intersect.
with our
cancel. They cancel. They all cancel out, and I get no electric field in the middle. Okay?
Other students that are
No big deal now, but when you guys get to APC, that's going to be a very big deal. Okay?
If you're not here for the purpose of
I think that's all we got.
please
Bye.
safely home.
Whoa! I hope nobody gets motion sick.